it's time for today's last lecture, which will be by Thamizharasi Tamizhmani, and we will hear about singularities of lattice equations. Thamizharasi, please.
I'm going to start from the conclusion of Vasil Grammaticos' lecture. We know that Paine-Levé equations, Paine-Levé analysis, Paine-Levé test, they dominated for more than 100 years in this particular part of mathematics. See, the singularity confinement test, what my collaborator Vasil Grammaticos mentioned, no? It is an analogous test for discrete equations. As in the Paine-Levé test for continuous setup, we consider the singularity confinement test for the discrete setup. And we were discussing about one case. I want to mention about that. Even in the Paine-Levé test case, linear equation, sometimes the test fails. The same thing happens in the case of discrete system also. So strictly speaking, Paine-Levé analysis and even the singularity confinement, we should consider only for integrable systems. Already linear systems are integrable, linear as well as linearizable systems are integrable. This work, as he said, we must throw focused on singularities of the system in order to get a full-fledged definition of singularity confinement test to lattice equation when we extend that to lattice equation. In my lecture, I am going to consider only the singularities of the well-known integrable system, KdV, discrete KdV and discrete modified KdV. This work is done in collaboration with B. Grammaticos, A. Ramani, J. Sakshma, D. Wum and R. Willox. Two of the collaborators are here. Okay, let me start the lecture. The discovery of singularity confinement, originally proposed by Vasil Grammaticos and Papageorgiou, they studied only discrete KdV equation over a small unit. See, look at that. See this M and N axis, as for your convenience, you can exchange vertically or horizontally. Okay. So in this particular square, here this is x and m plus 1, m axis here we have taken along the vertical line and n along the horizontal line. One particular form of discrete KdV equation is this. You know that from the continuous equations, you will get many discrete forms. That is why we say that discrete systems are more fundamental than continuous systems. In a way, you can get micro level information from the discrete setup. So when we consider this equation in a bounded domain, we found that what happens when you take x is equal to 0. So look at this. Yes. When you consider this 0, when you substitute that in the previous equation, you will get infinity here, here also infinity, and again, when you move up or come from this line, this point will be 0, again go to the next step, this is infinity, from here go vertically, again this is infinity, this, both the concurring lines, again this will be 0. So this is the pattern of the singularities that we get when we iterate the original discrete KdV that we have taken. So let's do the calculation. Start with x0, 0 as epsilon. Then when you compute that x1, 0, it will be 1 by epsilon. x0, 1 will be minus 1 by epsilon. x11 is minus epsilon. We have a pattern like this. We have a pattern like this. So here, when epsilon tends to 0, a singularity appears here, a singularity continues here, and here it disappears. But in the singularity confinement test, we want to get back the initial conditions also. We will go to that. we'll calculate x12 and x21. This is a singular rule already followed in numerical analysis. So you can write, avoiding this to infinities, you can write this x21 in terms of the other vertices over the 3 unit squares. Look at this. Here x21, x minus 1. We are avoiding the singularity. X minus 1, 0, 1 by x minus 1, 1. And then we are jumping to x2, 0. Similarly, we will get this condition. This is, as I told you, in numerical analysis, to avoid this infinity, it is calculated like that. When we calculate, we see that here it takes the value infinity. Here also it takes the value infinity. But when we move further, no, the indeterminacy is, rather singularity is removed. They are all finite values. So when we calculate x22, we have seen that it is also finite, but the expression is very complicated. How to, we will iterate the discrete KdV. Look at this. Initially, when we have 1 0, this is the pattern. When you have 2 zeros, this will be the pattern. And when we have 3 zeros, this will be the pattern. When you have 4 zeros, this will be the pattern. In every case, no, the singularity disappears. But this pattern grows. In all the setup, singularity essentially disappears. We will see this. So, we slightly perturbed the discrete KdV that we have taken. We have taken here alpha. And this type of singularity pattern is obtained only for alpha is equal to 1. Therefore, this is nothing but the discrete KdV case. This inspired the proposal for singularity confinement criterion. Things are much simpler when you go to the one-dimensional case. So consider a reduction like this. And after one integration, no, this discrete KdV reduced to this pattern in one dimension. If we take xn is equal to x0, you take this to be finite and take xn plus 1 is equal to 0. We find by iterating that xn plus y in the fifth iteration, it takes the indeterminate form. So instead of taking 0 directly, we consider xn plus 1 as epsilon, as he has done already. Do the iteration. So we will have xn plus 2 is equal to 1 by epsilon, xn plus 3 is minus 1 by epsilon, xn plus 4 is equal to minus epsilon, and limit of the concept is the xn plus 5 is equal to x0. Here the singularity appears, continues. It is disappearing, but the initial condition is not retrieved. So we go for one more iteration. Now we are retrieving the initial condition. In singularity confinement, two concepts are very important: lifting the indeterminates and recovery of degrees of freedom. In other words, initial condition is retrieved. But what is really meant by confinement in the lattice case? That is our question. How well do we know the singularities of discrete KdV? In the previous pattern, no, we have seen lines of infinity like this, lines of infinities, and parallel lines of infinities. We'll go to that figure. Look at that. Lines of infinities. Again, lines of infinities. Lines of 0 bordered on either side with lines of infinity. So these two are two normal types of singularity pattern for KdV. These are not the only pattern. This is type 1 and this is, first type of singularities, second type of singularities. But when we see the rewrite the equation in this particular form, when we make right hand side is equal to 0, the left hand side also equal to 0. So we get the product of these 2 points, no, it is equal to 1. It is like that everywhere. When you increase d, 1 by d decreases, so the full strip, horizontal strip will be points at infinity. So you get a horizontal strip of infinities. You can have even more than one horizontal strip of infinities. Instead of taking 1, if you take this as -1, then this horizontal strips will be vertical. So again, let us consider this singular rule as I told in the previous page. A band of singularities are appearing either horizontally or vertically, like that. We call this type of singularities as Taishi. This is the third type of singularities. What is more interesting is the interaction of this type of singularities with the other 2 types. It is very, very important. When we consider, look at this, in bounded singularity, even if you have, when this Taishi hits this particular point, it continues. There is this, in this box, the interaction is happening. Whereas in the lower part, if it hits this particular edge, you will have a copy of this down. Similarly, in the lowest strip, when it is hitting the edge, a copy of that above is created. Then the Taishi continues. So this is the interaction in the case of bounded singularities. Now we'll go to here. See here, look at this. When this Taishi hits this particular line, it continues. When it hits this particular line, this is pushed upwards, so upwards like this in the lower part, and for this also like this. A symmetric copy of this unit box, like that. So you are having symmetrically, for this you have a structure like this. What is more interesting in this is the interaction with the lines of infinity. So far we have studied only infinities in bounded inner domain. When we consider its interaction with infinite lines, look at this. This is a Taishi. When it interacts with this, it is moving 2 step upwards. This Taishi is moved 2 steps upwards. Let us consider the interaction with 2 infinite lines. This Taishi is twice. For this infinite line, moving 2 steps up, and again for this infinity line, again further it is moving 2 steps up. When we consider the second type of singularities, namely this, lines of zeros on either side bounded with infinite lines. Consider this Taishi. For this infinite line, it is moving 2 steps up. And for this 0 line, this will bring down 2 steps down. Again, for this infinite line, it will go up 2 steps up. So 2 minus 2 plus 2. Ultimately, it is moved only 2 steps up. So this is the interesting interaction of Taishi with the line of infinities in both the cases. Already this starts reminding of soliton interactions. So look at this. Action is happening here. After that it continues without any loss of generality. Similarly here also, this is the action zone, and here also this is the action zone, and it continues with the same structure. It gets more complicated when we introduce weights to the Taishis. We have taken so far this concept. Infinity is limit epsilon tends to 0 of 1 over epsilon. This we can write like this. Sometimes we can introduce weights also. Let us see what happens if we add weights. So Taishi of weight p, it takes infinity power p when we take the limit epsilon tends to 0 of 1 by epsilon power p. So this can be written, the product of the consecutive edges is equal to 1 plus order times epsilon q or p anything. This changes drastically the interactions. In the previous case, each Taishi is shifted 2 times upwards. But if we consider a Taishi, look at this. Oh, this we finished. Yes. When we consider a Taishi of weight 2, look at this, it is a Taishi of weight 2, and we consider line of infinities with weight 1. We have checked that this is shifting only 1 step upwards. Similarly, when we consider 2 lines of infinities, it is a Taishi of weight 2, a line of infinity of weight 1, so moved only 1 step up. Again, due to this line, it moves again 1 step up. When we consider this type of singularities, lines of zeros bounded by lines of infinities, when we consider the interaction, due to this infinite line, it moves 1 step up. And due to the 0 line, it comes downwards one step down. Again, due to this, it goes upwards 1 step. So accounting all the 3, 1 minus 1, then plus 1, ultimately it moved only to 1 step up. So here the Taishi is pushed only once upwards, whereas in the case of Taishi of weight 1, it is moved 2 steps upwards. There are new effects we have studied. I'm going to give one interaction setup. After that, when you work all these things, all the figures will be clear to you. Here, we are considering a Taishi of weight 3. It is interacting on an infinite line of weight 1. There is sufficient happens. One Taishi of weight 1 continues in the same direction, whereas another Taishi of weight 2 in the upward thing. So there is sufficient type of thing happening here in this case. Similarly, we have taken a Taishi of weight 3. So it is split into a Taishi of 1 in the same direction, a Taishi of 2 in a parallel direction. When you consider a Taishi of weight 5, we have observed that it continues in the next step, and a Taishi of weight 4 just above, 1 step above, and a Taishi of weight 1, 2 steps above. There is a fusion also. You consider 2 Taishis, here with weight 3 and here with weight 2. When you interact that with an infinite line of 4, you will get a Taishi of weight 5, 1 step above. As I told you, we will be doing some numerical calculation. After that, you will be clearly getting this idea. Again, transfer of weights can also happen. Look at this. You have one Taishi of weight 3, here another Taishi of weight 4. So total weight, this parallel, 2 parallel Taishis is 7. So when you do the interaction with an infinite line of weight 5, look at that. The first one is Taishi of weight 1. And because of this line, the remaining thing is a Taishi of weight 6. Here also 7, here also put together the Taishi weight is 7. Look at that, the infinite lines are shifted accordingly. We can do a complicated interaction like this. See, look at this, a Taishi of weight 1, a Taishi of weight 2, a Taishi of weight 4. Here there is no Taishi. Even with all this, you consider infinite line of weight 2 and another infinite line of weight 2 and another infinite line of weight 1. Due to all these interactions, you will get a complicated figure like this. You will get a clear idea when you do that calculation. So here I want to say that it goes complicated. We are not able to infer anything from the discrete KdV. So we want to do the same thing. One thing is clear now. The order is important. Interaction changes when you take the order into account. So we must keep an eye on the order. Let us study this for the discrete modified KdV in order to have better ideas. So the discrete modified KdV we have taken in this form. Again, it is one of the form of discrete modified KdV. Here we have taken k power 4 not equal to 1. So 1, k and 1 by k, no, they play the role of 0 and infinity. So here 0, here infinity, here 0, the same setup. Instead of considering 0 and infinity, we are considering k and 1 by k. That is the only difference. So here also you have infinite line of infinities. We have Taishi in this case, as we have in the discrete KdV. Look at this. Taishi will happen for this value. Look at this. And the interaction with the infinite line. See, this is something interesting. In the case of modified KdV, the Taishi is pushed only one step upward. Whereas in the case of KdV, the Taishi is moved 2 steps upwards. This is the major difference. As in the DK, I'm sorry. Okay. I'm always confusing with the next page and the pointer. Okay. Let us consider, we introduce weights as we did in the case of KdV. See here, a Taishi of weight 2. It is interacting with the line of infinity of weight 1. Again, there is a fission. A Taishi of weight 1 is continued in the same direction. Another Taishi of weight 1 is in the parallel direction. While in the discrete KdV, it is moved 2 steps above. We are working with a Taishi of weight 2 with an infinite line of weight 1. We have seen in the previous page that it is moved 1 step upward. All this can be explained in terms of symbolic dynamics. For the interaction of the Taishi with an infinite line of 1 by k with weight 1, start well below the lowest Taishi, move upwards up to the point of the lowest horizontal strip in the Taishi with non-zero weight. Subtract 1 from its weight and add 1 to the Taishi above it or the strip above the Taishi. Then move to the next horizontal strip, leaving these 2 strips till you reach a non-zero weight. So take 1 from that and add this 1 to the strip above it. Repeat the same procedure until there are no more Taishi with the strips with a non-zero weight left off. Suppose if the line of 1 by k is of weight p, you have to repeat this for p times. One important thing, the interaction of Taishi with lines of infinity comparatively simpler in modified discrete KdV than in discrete KdV. We can also do for KdV, only thing is, instead of considering an infinite line of weight 1, no, you have to consider infinite line of weight 1 by 2. In other words, for MKdV, you do this interaction only once. For discrete KdV, you have to do this for 2 times. That is the rule, okay? So here, look at that. This is 0 weight, this is 0 weight, the first non-zero weight. So we are removing 1 from that. And we are adding that one here. So we get this. This is for MKdV. Go to discrete KdV, 0 weight, first non-zero weight. Take 1 and add 1. So this will be like this. But as I told you, if you do once for MKdV, you have to do it twice for KdV. You go to the next step. So remove this 1. So this becomes 0. Add that 1 here. So it will be 2. So this is the interaction of with the KdV, and this is the interaction with discrete KdV for this Taishi. We have taken this as the Taishi. Very complicated interactions. You will first let me explain the numerical value, and then when you use this, the above figure will be clear to you. So we are taking a general Taishi with this, in this form. It is given by a vector 0, 0, 0, 6, 0, 2, 1, like that. See, look at that. We are going to do the interaction for the KdV. So as I told you, for the first line, where is the first line? So here it is the first line. So it is an infinite line of weight 2. So for each weight for KdV, we have to do 2 times. For this infinite line of weight 2, we have to do 4 times. So up to this for the first line, next 4 is for the next line, and the last 2 is for this weight, because weight is only 1, only 2 interactions. Let us continue. Look at that. Here non-zero weight, take that, add that to the above. This is 0. This is a non-zero weight. So take 1 from that, add 1 in the above. After that only 0. Stops there. Come to this section. So this here 0. Remove 1. So you have 2. Add that 1. The 0 becomes 1. Again this is non-zero weight. So we can take 1 from that. That 1 is added with this. So this becomes 2. Above values will be 0. Coming to this, it is 0, non-zero weight, remove 1, add that 1 here, again non-zero weight, remove 1, add that here, and then 0 weights. Go to the next one, non-zero weight, you remove that, add here in the next step, again non-zero weight, remove 1, this becomes 4, then 0, 0. Now coming to the next action, no, interaction in fact, 0, 0, this is non-zero weight. Yes, remove this, remove 1 from this, so 2, add 1 to this, so 3, remove 1 from this, so 3, add 1 to that, so you will have that. Come to the next interaction, 0, 0, this is the first non-zero weight. So when you remove that, it will be 0, add that with 4, it will be 5. Take again, this is non-zero weight, remove 1, this becomes 1, add 1, this becomes 3, and then 0. So similarly, the next, as I told you, for this line, these 4 interactions, and for the next line, this is the starting vector. So these 4 lines for this, and next 4 lines for this line, and so we are left out with the last line of weight 1. So we have to do 2 more steps. So coming to this 0, 0, 0, again I removed 1, added 1, removed 1, added 1. So here, remove 1, add 1, remove 1, add 1. So here also the first non-zero weight is 2, remove 1, this becomes 2, add 1, this becomes 4, remove 1, this becomes 0, and add 1, this becomes 3. We have to stop here because 4 plus 4 plus 2, 10 interactions. This is KdV. If it is in the case of MKdV, for each weight you have to do only one step, not 2 steps. But here for each weight we are doing 2 times. Okay, this discrete modified KdV, no, the shifting is in one step. So we can connect the box and ball representation to the modified discrete KdV. It is more interesting. So there is a box and ball representation for the Taishi interaction. You take the weight of the Taishi, call it as vector u. Then there is a carrier. The carrier's maximum capacity is 1. This V will not interact with 0 entries in U. Empty carrier at a position in U with the non-zero entry only it will interact. It will take one value from U, that carrier becomes full and it moves up. It gives that one to the next step upwards. So this carrier will be having 0 capacity and 1 is added to the value in U. This can be represented in this form. This is nothing but the famous Takahashi-Shachima system, box and ball system. So what we conclude here, the dynamics of Taishi has some relation with the ultra-discrete version of the equation. What I presented here is I have only scratched the surface. In order to proceed further, no, we need to have a lot of discussion. So let me conclude here and summarize what we have seen. Discrete KdV and MKdV, they have very interesting singularities. In particular, the Taishi type, we have never seen it before. It has very rich dynamics. The dynamics can be described by a set of very simple rules. The rules have a close relation to the box and ball system. The box and ball system is the ultra-discrete limit of KdV as well as MKdV. So the dynamics of the singularities of KdV are governed by the cellular automaton analog. So this is a very interesting point. Let me go to what are all the open questions or other lattice equations with similar behavior. We have to verify this. Can we give a rigorous proof of the symbolic dynamic of the Taishi? Can we find singular rules that describe the behavior of the Taishi? And going back to the starting point, what could be the singularity confinement for lattice equation? As I mentioned earlier in the beginning, no, this will give you some input before you define what is singularity confinement for lattice equation. Okay, we may expect the answer in the future. Yes, with this I stop.
Thank you very much. Are there any questions, comments?
Yes.
Go ahead.
So in the ultra-discrete limit, we see arising some sort of structure of solitons. So my question is, are there discrete solitons, even, and are they known, classified, understood?
Yes, sir. Statistical things are discrete things. Of course.
The ultra-discrete ones are actually just the ultra-discrete limit of the discrete ones.
In fact, all the practical things that we are seeing are basically discrete systems only. It is impossible to write that in the form of continuous setup. All practical problems are like that.
Questions, comments?
Yes.
Two of them.
So there is also discrete Toda equation representation of this box wall system. Can this be extended to?
You have studied discrete Toda in the singularities of discrete Toda? No, so far. We have studied this discrete KdV and modified discrete KdV because it's very interesting. Normally, no, even in the continuous case, they have taken only KdV equation as a ground example. Maybe one can try for this Toda equation. They are also integrable.
Taishi thing, this
kind yes, who knows? It may appear.
Okay.
Yes.
Thank you.
Even in the MKdV case, first type of singularities are there, but the second type of singularity we don't have, but we have Taishi.
There was another question.
The question is about the comment that she made in response to Philippe. I'm not sure. Is it expected that such a phenomenon can also appear in continuous model?
No such things. For all practical problems, no. See, for example, how many planes are crossing a particular place within 1 hour. You cannot continuously sit and watch. You will take the data only in finite intervals of time. Humanly, that is only possible. That is why we say that no, discrete dynamics is more fundamental than continuous setup. To study rigorously continuous setup is very interesting. But for every continuous system, there are many discrete systems. So you will have more information from the discrete system.
Other questions, comments? This time, if I may make a comment, it's not an answer to your question, the last question. It's not the same phenomenon, but there's a strong analogy. There's an old paper by Goncharenko and Veselov, maybe 20 years old, on the soliton interactions in matrix KdV, continuous matrix KdV. And they show that they actually satisfy the Yang-Baxter relation. Ordinary KdV, it's often said that it does, but actually it's not quite true. But in the case of matrix KdV, it is really the Yang-Baxter relation. Now, the box and ball system that is appearing here is just the dual of the normal one. So that the carrier now has capacity 1 and the boxes have infinite capacity. And that is really a degenerate case of the tropical Yang-Baxter map that is associated with modified KdV. So actually these interactions, they satisfy the Yang-Baxter relation in a very degenerate case. It's just an analogy, but if you're asking about a relation to the continuous world, for the solitons, well, yes, they also satisfy the Yang-Baxter relation in a tropical sense. Well, the singularities do as well. So that's, but if you, I mean, when I say the solitons satisfy the Yang-Baxter relation, that is true for the box and ball system. For discrete KdV, we don't know. I would say their properties are similar probably to the continuous KdV, and they won't. But the singularities do satisfy Yang-Baxter, and that's sort of, well, at least fun.
In fact, we are exploring the possibility due to some questions, no? Why singularity confinement is failing in certain cases. No, the point is we should study totally all the singularities of the equation. That is because you are getting information, no? Lot of information you are getting. This can be the input to study those equations. That's why I said when you want to define the singularity confinement test for lattice equation, all those things should be accounted. Maybe some more thing also may come in future.
If there are no other comments or questions, then let's thank Thamizharasi and all.
Oh, I finished early, huh?
There are still 5 minutes, so if you want to continue, then please continue. I mean, there still is time. No?
Maybe questions I can answer.
If there are,
yeah.
Are there any other questions? If not, then we end a little bit early. Thank you very much.
Okay. Welcome.